Hi, we are continuing with renal physiology. In this time, we are looking at reabsorption and secretion. There's nothing complicated about reabsorption and secretion, just from the terminologies, reabsorb. Okay, to reabsorb what was filtered. When something is filtered, it is bound to be excreted in urine. Okay, but reabsorption is what can we call it? Reclaiming what was lost. Okay, reclaiming what was lost back into the body. Now, secretion, it's what is in the blood. Now is what is in the blood, it is released into the renal tubules without passing through the filtration process. So these mechanisms are happening. Okay, there's another mechanism, filtration. These are the three mechanisms that we see happening in the kidneys: filtration, reabsorption, secretion. Filtration, reabsorption, secretion. Filtration, reabsorption, and secretion. At the end of the day, we are producing a urine, okay, which is a waste product, waste fluid, which is removed out of the body. Okay. So, glomerular filtration results in the production of large quantities, about 180 liters per day, of an ultrafiltrate of plasma. Okay? Now, if this ultrafiltrate were excreted and modified, would lose a lot of important substances. Okay, would lose 180 liters of water, we lose 25,200 milliequivalents of sodium, we lose 19,800 milliequivalents of chlorides, we are going to lose 5,320 milliequivalents of bicarbonates, we will lose 440 milligrams of glucose. This is not going to be a normal body, okay? When such happens, we are inviting death. So, each of these losses represent more than 10-fold of the amount present in the entire extracellular fluid. Okay? When we lose these electrolytes, homeostasis mechanisms will be disrupted. All the physiological processes that depend on this mechanism will be disrupted, like action potentials, active transport mechanism, and many other biosynthetic mechanisms will be disrupted. So, fortunately, reabsorptive mechanisms in the epithelial cells lining the renal tubules return these substances to the circulation and to the extracellular fluid. Okay? In addition, if there was no secretion, there will be accumulation of toxic materials in the body, which would depress the entire body. So, secretion mechanism in the epithelial cells remove certain substances from the peritubular capillaries and add them to urine. Okay. Now, measurements of reabsorption and secretion. This diagram is illustrating the processes of filtration, reabsorption, and secretion. And also the glomerular capillary has been shown with the afferent arterioles and the efferent arterioles. And then there's an initial part, which is the Bowman's space, and the beginning of the proximal tubules. They have been shown there. Okay, and then the epithelial cells lining the renal tubules have been shown. And then there is a nearby peritubular capillary. It has been shown there, which emerges from the efferent arterioles, as you can see, and supplies the blood to the nephron. Okay. Now, when you look at filtration, an interstitial type fluid is filtered across the glomerular capillaries into the Bowman space. Okay, the amount of substance filtered into the Bowman space per unit of time is called the filtered load. Okay, The amount of substance filtered into the Bowman space per unit time is called the filtered load. The fluid in the Bowman space and in the lumen of the nephron is called the tubular fluid or the luminofluid. Okay. And then the other thing is the reabsorption. Water and many solutes. When I say many solutes, like sodium, chlorides, bicarbonates, glucose, amino acids, phosphates, urea, calcium, magnesium, lactate, citrates. Many solutes are reabsorbed from the glomerular filtrate into the peritubular capillary blood. Okay, so the mechanism for reabsorption involve transporters in the membranes of the renal epithelial cells. So the mechanism of transportation is just the same mechanism we described earlier when we started physiology. It can either be active transport, which we have primary active transport or secondary active transport. It can also be via diffusion. So, if reabsorption did not occur, most of these substances will be removed and lost in urine. And there will be problems. Okay. And then we have secretion. Now, a few substances, example, organic acids, okay, mainly hydrogen ions, and organic bases, and potassium. Remember, I've mentioned three things. Substances which are usually excreted, these are organic acids, organic bases, and potassium. These are secreted from the peritubular capillaries into the tubular fluid. Therefore, there is an addition to the filtrate, other substances. Okay. So secretion provides a mechanism for excreting substance in the urine, especially if that substance did not get filtered or that substance is too toxic. And then there is this excretion. Excretion or excretion rate. Here there is no redemption. There's no taking back of the substance. Once it's in the excretory load, there's no going back into the body. So excretion is the net result of these three processes. Okay? It is the net result of these three processes. So we can show them in form of an equation. Excretion is equal to secretion plus filtered load minus reabsorption. As simple as that. So the excretion rate can be compared to the filtered load to determine whether a substance has been reabsorbed or secreted. Now there's a formula that relates these things I've just talked about: filtered load, reabsorption, secretion, and excretion. This is the formula. This formula is used to calculate filtered load, excretion rate, and reabsorption or secretion rate. So filtered load, okay, filtered load, I said that filtered load, this is the volume or the amount of substances filtered into the Bowman space. It is equal to the glomerular filtration rate times P, which is the amount of substance of the particular substance X in plasma. And then the excretion rate, this one is urine, is equal to V, which is the urine flow rate, times U, the amount of particular substance X in urine. Okay, just think about this equation. You're going to see that it makes a lot of sense. It makes a lot of sense. So we can look at this example of net reabsorption of sodium. Example of net reabsorption of sodium. What is this diagram showing? Example of net reabsorption of sodium. Okay. Filtered load of sodium is equal to glomerular filtration rate plus the concentration of sodium in plasma, which is 140 milliequivalents per liter, over 180 times 180 liters per day, which is the glomerular filtration rate. So you're going to calculate the filtered load. The amount of sodium filtered is 25,200 milliequivalents per day. Now, excretion also has a formula, and it is dependent on the urine flow rate. Okay, the amount of urine that you have produced in a particular period of time. Usually you can calculate it in 24-hour period. So for example, you have produced 1 liter per day, and we know that the concentration of sodium in urine is 100 milliequivalents per liter. So the answer you find is 100 milliequivalents per day. Now, the question you may ask yourself, look the amount which was filtered, but look the amount which was in the urine, meaning that a larger percentage of it was reabsorbed, which is this 25,100 milliequivalents per day. So this is the application of these equations. Okay. Now, look at this other one. Example, net secretion of PAH. Filtered load of PAH is 180 liters per day times 100 milliequivalents, which gives you 180 grams per day. Excretion rate, if you incorporate this equation, it will give you 1 liter per day times 54 grams per liter, which is 54. Now, look, there was only 18 which was filtered, but it has increased to 54. Where has this 54 come from? It's because of secretion. Okay? So secretion is 36 grams per day. Okay. We're still looking at reabsorption and secretion. Now, glucose is one of the most important nutrients in the body. How is it absorbed? Glucose is reabsorbed by secondary active transport. From this diagram, you can see that glucose moves from the tubular fluid, okay, into blood through the sodium glucose transporters. And then at the basal electrocyte, we have sodium pumping out, potassium going in, and then glucose through the glucose transporters, it moves into blood via facilitated diffusion. Okay, so this one is called the sodium glucose transporters. Let me just repeat. This one is called the sodium glucose transporters, and then this one is called the glucose transporters. So these glucose transporters can either be GLUT1 or GLUT2. Okay, and they transport glucose by facilitated diffusion. Away from that, there's this concept called the glucose titration curve. Don't get confused. Glucose titration curve, it just depicts the relationship between plasma glucose concentration, this one, and glucose reabsorption. And glucose reabsorption. So in a normal healthy person, this is what we expect, this graph. In a normal healthy person, as the plasma glucose, this graph, what it means, as the plasma glucose keeps on increasing, okay, the absorption rate will also increase, but to reach a point here where the absorption rate will remain constant. That is called the transport maximum. Okay? The transport maximum for glucose, which is also called TM, it has been estimated that the transport maximum is about 375. Okay? The transport maximum for glucose is 375 milligrams per deciliter. or let's not use deciliter because we are dealing with time. Maybe let me repeat so that you follow me clearly what I'm trying to say here so that you don't get lost. This is called the titration curve. Okay, it shows the relationship between the amount of glucose in the blood and what can actually be reabsorbed. So the filtered load, we know that glucose is freely filtered across the glomerular capillaries, and the filtered load is the product of the glomerular filtration rate and the plasma glucose concentration. Okay, and then we know that reabsorption at plasma glucose concentration less than 200 milligrams, all the filtered glucose can be reabsorbed. Okay. Excretion, to understand the curve for excretion, this one, we need to compare the filtration and the reabsorption. So below the plasma glucose concentration of 200 milligrams, below the plasma glucose concentration of 200 milligrams, all of the filtered glucose is reabsorbed and none is excreted. However, when there is at plasma glucose concentration above 200 milligrams, the carriers are becoming saturated, the glucose transporters. So most of the filtered glucose is the glucose transporters and the sodium glucose transporters, they are becoming saturated. So most of the filtered glucose is reabsorbed, but some is not. The glucose that is not reabsorbed is excreted, and it appears in urine. Okay, because it has the plasma concentration at which glucose is first excreted in urine is called the threshold, which is 350 milligrams per deciliter. Okay. So above 350 grams per deciliter, transport maximum is reached. Okay. And the carriers are fully saturated. And if you can see, the graph will continue linearly as a function of plasma glucose concentration. Okay, so here there's nothing much. We're just showing that usually in a normal health person, we expect this curve. And we expect this curve. But in people with diabetes, you find that the levels of glucose appears in the blood, in the urine, because the glucose transporters have become saturated. Okay, so at normal plasma glucose concentration, all the filtered glucose is reabsorbed and none is excreted. Under some circumstances, however, glucosuria may occur. So I've put this diagram just for you to appreciate sodium reabsorption. They are straightforward. On the first column, I've shown the nephron segment, the mechanism by which sodium is reabsorbed, and how it is regulated. Okay, what factors can influence sodium reabsorption, or what factors can inhibit sodium reabsorption? When you see a positive, it means that factor can stimulate. When you see a negative, that factor can inhibit. So just run through these solutes. Okay. Potassium secretion, bicarbonate secretion, water reabsorption, phosphate reabsorption, calcium reabsorption. So this diagram showing you how the kidney handles these electrolytes, such that at the end of the day, we are going to have a urine concentration like this. As you can see, there is no glucose in urine, there is no amino acid in urine, there are no proteins. So in summary, what we are trying to say is that glomerular filtration, the plasma is filtered in the glomeruli, and the substances reach the renal tubules along with water as filtrate. In tubular reabsorption, the 99% of filtrate is reabsorbed in different segments of the renal tubules. In tubular secretion, some substances are transported from blood into the renal tubules. With all these changes, the filtrate becomes urine. Okay, so we'll end here. Thank you very much.